Okay, so what is configuration and there are two types of configuration we study. Next we have conformation. So conformation also involves isomerism only. So today we will finish isomerism topic. Tell me, first is configuration. So what is the meaning of configuration? The arrangement of atoms or group of atom around the asymmetric carbon, right? The arrangement of atoms or group of atoms around the asymmetric carbon is nothing but configuration. It is a spatial, of course, the spatial arrangement of atoms or group of atom around the asymmetric carbon is called configuration. Then there are two type of configuration. One, absolute configuration, which is also called RS configuration. This is also we don't study in +1, +2 level. It is there for only NEET and JEE. Next, second one is relative configuration. Okay, it is also called capital D, capital L configuration. This configuration we have studied in biomolecule topic, DL. Okay, anyway, once again we will do both. Tell me, so what is RS configuration and its example, and DL configuration its example? Write down first. Configuration, the spatial arrangement of atoms or group of atoms, the spatial arrangement of atoms over or group of atoms around the asymmetric carbon, is called configuration, Next, types of configuration. 1, absolute configuration in bracket RS configuration. 2, relative configuration DL configuration. So let us see first absolute configuration. Okay, right. Okay, this absolute configuration was given by Kohn-Ingold Prelog, where we have studied in EZ nomenclature, right? So it is proposed by Kohn-Ingold and Prelog. Okay, and given the CIP rules. What are the CIP rules? Kohn-Ingold Prelog rules. Okay, right on. It is developed by Kohn-Ingold and Prelog. It is developed by Kohn-Ingold and Prelog. Right? CIP rule or systematic rules, or it is also called sequence rules. Sequence rule. Okay, right. First rule, identify the atoms or group of atoms. Identify the atom or group of atom present on asymmetric carbon. Identify the atoms or group of atoms present on asymmetric carbon, and give the priority based on atomic number or atomic mass. Give the priority based on atomic number or atomic mass. Okay, for example, let us take, it is a, take down simple molecule Tell me. In CIP rule, the first rule is first identify the asymmetric carbon. Tell me, this is asymmetric carbon, right? Now this asymmetric carbon having 4 different groups: hydrogen, OH, aldehyde and methyl group. Therefore identify the groups or atoms present on the asymmetric carbon and assign the priority or give the priority. It is based on atomic number or atomic mass, as like EZ nomenclature. Tell me, in EZ nomenclature we have given the first priority to what? More atomic number or atomic mass. Tell me, which is more atomic number? This carbon attached to oxygen, carbon, hydrogen, carbon, 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 carbon. Therefore carbon hydrogen is 1. Next, second priority, carbon, carbon here, carbon to carbon. So therefore now if this asymmetric carbon attached to same atoms, then see the next atom for priority, same rule. So what is the next atom here? 3 hydrogen, this is actually aldehyde group, no? Now this aldehyde group can be taken as what? 2 oxygen, 1 hydrogen. It means, so this carbon atom attached to 2 oxygen, 1 hydrogen, here 3 hydrogen. Therefore second priority goes to aldehyde group, third priority goes to methyl group and fourth priority for hydrogen. So therefore this is the first rule: identify the atoms or groups on asymmetric carbon and give the priority. Okay, next, second rule. Second rule is connect the 1, 2, 3 priority groups. Connect the 1, 2, 3 priority groups. Then down write A. If it is clockwise direction, called R configuration. If it is clockwise direction, called R configuration. In bracket, fourth priority group must be on. In bracket, fourth priority group must be on vertical column, vertical line. Fourth priority group must be on vertical line over R. Vertical line equal to what? Below the plane tane, or below the plane. B. If it is anti-clockwise direction, B. If it is anti-clockwise direction, then it is called S configuration. Then it is called S configuration and fourth priority group must be where? Same. Fourth priority group must be on vertical line or below the plane. Okay. Only these 2 rules. Now tell me. So what is the what is the configuration? See, now first rule is already we did here. Now next, second rule is what? Connect the 1, 2, 3. It don't bother about fourth position. It just connect 1, 2, 3. 1, 2, 3. It just connect 1, 2, 3 like this. Then this 1, 2, 3 clockwise, anti-clockwise? It is anti-clockwise. If it is anti-clockwise, the configuration is called S configuration. But condition is what? The fourth priority group must be on vertical line. This must be on vertical line or below the plane. It is vertical line, therefore it is S configuration. Right? Understand? Next, one more example. Do it fast. Tell me this. So give the priority. It is 1, 2, 3, 4. and connect the 1, 2, 3. You need not to bother about fourth group, where it is 1, 2, 3, it is clockwise direction, and fourth priority group must be on vertical line, therefore it is R configuration. So therefore usually the meaning of R is rectus, means it is right side clockwise. S is sensor, anti-clockwise. Rectus, sensor. Like E is a EZ, Z is a Zuzamen, E is a Ent Gagan. Like similarly, rectus, sensor. R is a rectus, clockwise direction. Rotation, clockwise direction. S is a rotation, anti-clockwise direction. Next, one more example. Bega, make it fast. Tell me. So now give the priority for this. Oxygen 1, next CO2, carbon 3, 4. 1, 2, 3. So fourth priority group must be on vertical line, therefore it is on vertical line, therefore it is a S configuration. Next tell me this. 1, 2, 3, 4. So clockwise, therefore it is a R configuration. Can you tell me what is the relation between these two? Very good. Non-superimposable mirror images. So therefore actually these two are non-superimposable mirror images. They are enantiomers. Therefore remember, for enantiomer, one enantiomer is S, other should be a R. It means enantiomers differ in their configuration. No, they have opposite configuration. Okay, I'll give that note later. So next is, so here there are two asymmetric carbon. This is one asymmetric carbon, it is another asymmetric carbon. Now first one oxygen, tell me next. Second has to be given COOH, and third is this, fourth is this. Tell me 1, 2, 3. No, 1, 2, 3. Okay, now but here fourth, now tell me it is anti-clockwise. If it is anti-clockwise, it should be yes, but where the fourth priority group? Fourth priority group on horizontal line, it should be on what? Vertical line. Therefore if you make it vertical line, the configuration become reverse. That's what. So this is actually anti-clockwise, supposed to come yes, it become R. Remember like this. It is anti-clockwise, is supposed to get R, that is S. But fourth priority group on horizontal line, if you make it is vertical line, the configuration become opposite. That's what, without making this conversion, you can get it opposite. Next, tell me, here is oxygen, COO, then this is 3, it is 4. 1, 2, 3. It is anti-clockwise, but where the fourth priority group? Horizontal, therefore it is R. Therefore RR is the configuration, like that. See, these two are actually enantiomer. No, enantiomer. Tell me, enantiomers must have opposite configuration. If it is a RR, it must be yes. You do it, you will get SS. right? ಇದು ಎಷ್ಟು ಬರುತ್ತಾ ಆ್ಯಂಟಿ ಕ್ಲಾಕ್ ವೈಸ್ ತಾನೆ. If it is anti-clockwise but fourth periodic group where horizontal, that's what actually you should get S, but horizontal no, that's what R. SS ಬರುತ್ತಾ, SS ಬರುತ್ತೆ ನೋಡಿ. ನೋಡಿ 1 2 3 ಇದು 1 2 3. Yes or no? Both are clockwise, but fourth periodic group on horizontal line. Next, so identify RS. Aldehyde is 1, this carbon 2, this carbon 3, it is 4. Connect 1 2 3 clockwise, and fourth priority group on below the plane, away from the observer, that is R. Next, 1 2 3 4. Again 1 2 3. You need not to take this fourth periodic group, you just connect only 1 2 3, neglect 4. 1 2 3, 1 2 3 is again clockwise, fourth periodic group is away from the observer, that is R. ऐसा clockwise R. Next, so here carbon carbon carbon, all three are carbon only. Okay, now tell me, so here carbon attached to carbon, here also carbon, but this carbon attached to another carbon, but this carbon attached to carbon carbon. How many carbon? Yes or no? 2 carbon. Therefore this is 1, it is 2, it is 3, it is 4. So therefore what is the connectivity? 1 2 3. It is S configuration. Next, chlorine 1, right? So here carbon attached to carbon, here carbon to carbon, this carbon attached to another carbon, not oxygen, this carbon attached to another carbon, that is also same. This carbon attached to carbon, this is oxygen, therefore 1, that is 2. Next 3 4. So connect 1 2 3, 1 2 3. How it is? Anti-clockwise, but where the fourth periodic group? It is above the plane, therefore R. Okay, so take one question. Identify the capital R, capital S configuration of following. Okay, will you? Tell me, here there are two asymmetric carbon, 1, 2. So what is the configuration of first asymmetric carbon? Yes, sir? Yes, R. Got it, all of you same? Next is R. Yes, R, R, S. First is R. Second one is RS. Next, so here is a glucose 1, 2, 3, 4. Right? There are 4 asymmetric carbon. 4 asymmetric carbon having like different. It may be same configurations. Okay, you do it later. This part you do it later. Next, okay. Take one note. ಹೇಳಿ. Not RS. Shall I do it? Okay, I'll do it. Chlorine is 1. This is 2. This carbon 3. Hydrogen 4. So connect 1, 2, 3. 1, 2, 3 anti-clockwise. But fourth periodic group on horizontal line. Therefore, R. Next, here bromine is 1. This CO is 2. Then this is carbon 3. Hydrogen 4. So 1, 2, 3. It is anti-clockwise. Clockwise, but fourth periodic group on horizontal line. Therefore, yes, correct then? Correct only. Tell me. Third one. Hydrogen, carbon, carbon, carbon. If there are all carbon atoms, which carbon gets more priority? Say this carbon, hydrogen. This carbon attached to one carbon. This carbon attached to two carbon. Why? C double bond C is equals to what? 2C. ಹೌದಾನೆ ಇವನ್ನ ಅರ್ಥ ಆಗಿಲ್ಲ ನನಗೆ. This is 1. this is 2, it is 3. First study EZ nomenclature. Based on EZ nomenclature, I have given 2-3 questions tomorrow exam. Tell me, this is 1, 2, 3. So it is a anti-clockwise and H is horizontal, therefore R. Then remaining will do. Martira? Okay, take note. So note is, it is interconversion. First point, right? Interconversion of groups on asymmetric carbon. Right, interconversion of the groups on asymmetric carbon. Then how to interconvert the group on asymmetric carbon? Okay, 1. There are 2 cases. Case 1, listen. In case 1, suppose let us take a asymmetric carbon having aldehyde group or else carboxylic group. Here is a H, this side is a OH, here is CH3, which is called lactic acid. Okay, tell me. Now what is the configuration? 1, 2, 3. 1, 2, 3 tane. How it is? Clockwise. Where is H? Horizontal. Therefore it is yes. You will get a config. Okay, 1, 2, 3, 4. 1, 2, 3. It is a S configuration. Okay, but now I want to make this horizontal line you bring into vertical line. How to do? Okay, actually we have to do that. Then we have to take. Okay, if you do, how to do here? See, remember, if the groups are present on horizontal lines, if you want to make it on vertical line, so you can turn by holding this group, by holding the top group, you can interchange the all 3 groups. How? Hydrogen you bring here, methyl you bring here, this OH bring here. Okay, so here what is the condition? Hold the top group, right? By holding top group and rotate the 3 groups. Okay, then you will get similar structure. Okay, so similar structure can be obtained by two interchange. First interchange is by holding the top group, so remaining through 3 groups can be rotate either clockwise or anti-clockwise. But I want to bring this H on vertical, that's what, rotate clockwise. Then hold the top group, rotate the remaining groups in clockwise direction. Tell me, when you rotate remaining groups in clockwise direction, then COOH will be same position, hydrogen comes here, then OH comes here. Tell me, here is methyl, right? Now see the configuration. 1, 2, 3, 4. What do you get? Tell me. 1, 2, 3. Yes or not? Yes. Same or not? That means the molecule configuration will be same. How? When by holding the top group and rotate remaining groups either clockwise or anti-clockwise. This is one operation. Okay. Next, similarly, one more. If the COOH is present top and H is present here, OH is here, CH3 is here. Now tell me, what is the configuration? 1, 2, it is 3, 4. Tell me quickly. It is configuration R. Okay. Now configuration R, how it is R? So therefore what you do is, now this hydrogen is bring here and holding which group? Holding top group constantly, then remaining groups rotate now left side anti-clockwise. Therefore, hydrogen bring here, methyl bring here, and OH bring here, and this COH group should be constant, don't disturb it. So therefore, then what do you get? COOH, and down H comes, this is OH comes here, CH3 come. Now see the rotation, 1 2 3 4. So what is the direction? 1 2 3 clockwise, that is R. Same or not? Same. It means, now question is like this, then when do you get same structures? The same structures can be obtained by holding the top group and rotating remaining group in a exchanging the remaining groups either clockwise or anti-clockwise, which gives same structure. That is one. But in our exams, most of the time question they will give like this, what is the relation between these two? They will give these two structures. By giving these two structures, what is the relation between these two? Enantiomers, diastereomers, homomers. Okay, something other option will be there. They are actually homomers. It means homomers means same actually. Both are same only. Why both are same? Both are having same configuration, right? If any molecule having similar configuration, the molecule must be same, right? Therefore, if you take A molecule, B molecule, what is the relation between A and B? A and B are not different, they are actually homomers, they are same. Therefore, homomers will have same configuration, and the relation between these two also, they are actually same, homomers. So homomers will have same configuration. Okay, this kind of question can be expected. So therefore, here you have to remember how to get homomers. Homomers can be obtained by holding top group and rotating remaining three groups either clockwise or anti-clockwise. That is case 1. Next, second case. Have you written this? Write down. Interconversion of groups on a symmetric carbon. Write case 1. Homomers can be obtained by holding the top group and rotating remaining groups either clockwise or anti-clockwise direction. So example 1, example 2. Next, case 2. Take the example. Second case. Second case, homomers also obtained by rotating all the groups in 180 degrees. Okay, let's see example. Tell me, what is its configuration? OH, COH2, no, it is CH3. It is 3, 4. So what is the rotation? 1, 2, 3. Okay, so fourth priority group on vertical line only, no. Therefore, it is a clockwise R. But now I want to interchange all the group 180 degrees. How? It means I want to bring this H down. Why? In Fisher projection, which group should be written on top? Most oxidized group. most oxidized carbon should be placed on top. That is the condition in Fischer projection. Therefore, now I want to bring this group here. Then what to do? This H bring here. So 2 are 180 degrees. Similarly, then this methyl bring here and OH bring here. If you rotate these two, you should rotate all. It is not mean that if you rotate these two, you will get same structure. No. Rotate ಮಾಡಬೇಕಾದ್ರೆ ಎಲ್ಲ ಗ್ರೂಪ್ rotate ಮಾಡಬೇಕು, ಸೇಮ್ ಬರುತ್ತೆ. ಎರಡೇ ಮಾಡಿ ಇದು ಬಿಟ್ಟರೆ ಆಗಲ್ಲ. Again structure changes. Therefore, rotate all the groups 180 degrees or interchange all the groups with 180 degrees. Okay, then you will get again homomer. So therefore, it is rotating all groups in 180 degrees. Tell me, by rotating all the groups in 180 degrees, carboxylic group come top, H come bottom, CH3 come here, OH comes here. Now see the rotation. It is 1, 2, 3, 4. 1, 2, 3. What is? R. Same or not? Therefore, homomers can also be obtained by rotation of all the groups in 180 degrees. Okay. Now suppose if the question is given like this, it is a aldehyde group, this is alcohol, it is a H, it is a CH2OH. Now tell me, question is identify the configuration, whether R or S. Okay, to identify the configuration, what we have to do? First of all, we need to see that fourth periodic group. Okay, fourth periodic group. This fourth periodic group should be where? It should be on vertical line. Okay, so therefore first interchange the group. It means you bring it vertical line. By how it is possible? By holding aldehyde group. So therefore this H bring here, this group bring here, this group bring here. Therefore aldehyde group come, it will be as it is, and this is OH, here is CH2OH, it is H. Now identify the groups, that is 1, 2, 3, 4. Now tell me, it is 1, 2, 3. How it is? Clockwise. This is R. It means, but here we get no, actually no, what it is? Connect 1, 2, 3. 1, 2, 3. How it is? Anti-clockwise ane? Anti-clockwise. It is anti-clockwise, but we have written R. Why? So instead of doing this, I told that you need not to do that. You take opposite. Right? That is, you will get R only. So therefore, if the question given like this, you have to change like this, you have to do actually. But without changing also you can get, that means if it is on horizontal line, you take it opposite direction. That's it. That is the shortcut method. Right? Understood? Next is, but as I told you, our questions are based on 3 important terms: homomers, enantiomers, diastereomers. Okay, so this is also right under note only. Under note only 1 or A. Homomers will have what? Same configuration. Homomers will have same configuration. 2. B. What about enantiomers? Enantiomers will have opposite configuration. One enantiomer is R, other must be yes. Right? Enantiomers will have opposite configuration. And what about diastereomers? Diastereomers. See, diastereomers will have same configuration at one carbon, opposite configuration at another carbon, right? So diastereomers will have same configuration at one carbon and opposite configuration at another carbon. Tell me. If there are more than 2 carbons, so that example we don't have in our syllabus. Okay, because we have only tartaric acid. Example for diastereomer, tartaric acid. Example for enantiomer, lactic acid. ಎರಡು ಇರೋದು, ಅದ್ರ ಬಗ್ಗೆ ಯೋಚನೆ ಮಾಡೋದು ಬೇಡ, ಇದ್ದಿದ್ದು ಓದಿದ್ರೆ ಸಾಕು. Tell me, question is, right question. What is the relation between following? Okay, relation between these two. ಮಾಲಿಕ್ಯೂಲ್ ನೋಡಿದ್ರೆ ಅರ್ಥ ಆಗಲ್ಲ, ಕಾನ್ಫಿಗರೇಷನ್ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳಿ. Tell me. Okay, what is the configuration? RR. Therefore, these two are homomers. It means actually both molecules are same. Huh? Enantiomer. Why? First one is what? R. Second is yes. Therefore, they are enantiomers. Next. Tell me. Diastereomers, correct only. How this is? RIS. R. This is? Yes. This is? It is R. This is? Huh? Hmm? R. Homers, huh? If it is homomers RS, it should be RS. Right. If it is enantiomer RS, SR. It is a diastereomer. Diastereomers differ. No, they have one carbon, same configuration. Understand? Diastereomers will have same configuration at one carbon. R and R, same configuration. And another carbon is opposite configuration. That means they are diastereomers. So therefore, question can be expected like this only. Either last one. Sure. You know, sorry. Whether they are enantiomers. What is the configuration? R. Yes. Here is yes. R. Enantiomer. Do you remember? Enantiomers are what? Optically active. Optically active. Optically active. D and L called enantiomers? No. Optically active. Whether it is optically active, these two are? Why? Huh? They are actually mesochromer. They are optically inactive. It is optically inactive. It is optically inactive. Therefore, they are not, even though configuration is opposite, they are actually homomers. Remember, because both are having what? Plane of symmetry. Because of presence of plane of symmetry, they are not actually they are supposed to get enantiomers, but they are not enantiomers because they have plane of symmetry. They actually what? Homers. Okay. So this is one condition, remember. Plane of symmetry. Right. Next, relative configuration, DL configuration. So this relative configuration DL we have studied in a biomolecule. Okay, in biomolecule we have studied that. So relative configuration, particularly now this is used for aldehyde, used for a biomolecule, that is carbohydrate and amino acids. Okay, tell me. So to assign the relative configuration, DL configuration, the simplest carbohydrate glyceraldehyde is taken, right? The simplest carbohydrate glyceraldehyde is taken. So glyceraldehyde structure is this, right? In glyceraldehyde there is a one asymmetric carbon, right? On asymmetric carbon, if OH group is right side, which is called capital D, that is a D-glyceraldehyde, right? D-glyceraldehyde. Okay, here no meaning for D. Remember, this D is not dextro-levo. Small d dextro, small l levo-rotatory. Capital D configuration, it has no meaning. Then next is, if asymmetric carbon OH is right side, left side, this is called, so capital L glyceraldehyde. So therefore, to assign the DL nomenclature, glyceraldehyde molecule taken as a standard molecule. In glyceraldehyde molecule, if OH group is right side, that is a D, H is left, OH is left side, that is L. Okay. Then next is, now this same nomenclature is applied to the other carbohydrate, for example glucose. And tell me, in case of glucose, tell me, glucose contain more than one OH group. If the molecule contain more than one OH group, then highest asymmetric carbon should be considered. Which is the highest? First, second, third, fourth, fifth. This is asymmetric carbon. Highest means last asymmetric carbon. OH is right side. Therefore, this is called D-glucose. So D, it doesn't indicate dextroglucose. Of course, glucose dextrorotatory, but actually it is written D plus glucose. D plus glucose. This D indicate configuration. This plus indicate rotation. That is dextrorotatory. Okay. So this is we have studied. Take 1 2 example enough. Next is conformational isomerism. Done. Conformational isomerism. Okay. So what is conformational isomerism? See, now so far we have studied what is structural isomerism. Okay. Isomerism basically two types. One is structural, second one is stereo. Stereo isomerism further classified into two types: configurational, conformational. So far we have studied configurational isomerism. Cis and trans and optical, all these comes under configurational isomerism. Then we will study conformational isomerism. So what is the difference between conformational, configurational? Configurational isomerism differ in configuration. We have studied DL configuration or RS configuration. They differ in configuration. And conformational isomerism, they differ in conformation. Then what is the meaning of conformation or conformational isomers? See, conformational isomer is the isomers which are formed by rotation of carbon-carbon single bond. The rotation of what? Carbon-carbon single bond. Let us take alkane. We know that all alkane having carbon-carbon single bond, right? In case of alkane, they are having carbon-carbon single bond and they are freely rotate. They can freely rotate around the carbon-carbon single bond. By rotation of carbon-carbon single bond, you will get infinite number of isomers. Okay, you rotate in small degrees, 1 degree, 2 degree, 3 degree. By rotating a small degree, you will get one new isomer. So all those infinite number of isomers are called what? Conformational isomer, and this phenomena called conformational isomerism. Therefore, what are conformational isomer? The isomers which are formed by rotation of carbon-carbon single bond. Therefore, in this isomerism we will study rotation of carbon-carbon single bond. Okay. Then next is conformational isomers. Isomers are formed by rotation of carbon-carbon single bond, and we will study conformational isomerism in ethane, N-butane, and another is 1, 2 butane 2-ol. 1 butane 2-ol. 1, 2 butane 1, 2 diol. We will study in 3 molecule. So one is we will study in ethane, second one is N-butane, and another molecule is but 1, 2 diol. Okay. In these 3 molecules study. If you understand ethane, the remaining are exactly similar. Okay, read on. Conformational isomerism. Right. The isomers which are formed by the isomers which are formed by rotation of carbon-carbon single bond, rotation of a carbon-carbon single bond called conformational isomers, and this phenomenon is called conformational isomerism. Conformational isomerism. Okay. See here. Now there is a one important difference between conformation configuration. Okay, we have taken this configuration. You see, D-glyceraldehyde. D-glyceraldehyde has only one configuration. This is the configuration D. But this D-glyceraldehyde may have infinite number of configurations. How? For example, you say carbon-carbon. You take this carbon-carbon bond. By rotating carbon-carbon bond, you can get n number of conformational isomers. So it means a given molecule has only one configuration, but conformations are many. Because by rotating carbon-carbon, single bond, by rotating a small degree, you will get, one isomer. So therefore, conformational isomers are many, but configuration should be only one. Right? Next slide. A given molecule has only one configuration. A given molecule has only one configuration, but infinite number of configurations. Sorry, conformations. Infinite number of conformations. Okay, next, conformational isomerism in ethane. Conformational isomerism in ethane. Right. So what is the conformational isomerism in ethane? Okay. Now let us take, this is the ethane molecule having carbon-carbon single bond. Okay. Now listen. In ethane molecule there are only two carbon. By rotating this carbon-carbon single bond like this, by rotating carbon-carbon single bond, you will get infinite number of isomers, that is called conformational isomers. Out of infinite number of conformational isomers of ethane, there are two are important. Only two conformations are important. Those are: one, eclipsed conformation. Second one is staggered conformation. So therefore, ethane gives n number of conformational isomers, but out of n, only two are important. One is eclipsed and staggered. Then what about remaining all? Other than these two, remaining all are called skew conformations. Okay, those are not important. So other than these two, whatever the conformation you will get, those are called skew conformations. Okay, now let us say what is eclipsed and staggered conformation. Then to understand eclipse and staggered conformation, you need to understand first representation of conformation. Then conformations can be represented by two methods. One, Sahar's projection, Newman projection. So therefore, all the conformations can be represented by two methods. One is a Sahar's projection. In Sahar's projection, we take the vertical column. This is indicate carbon-carbon single bond. Vertical line indicate carbon-carbon single bond. Take carbon-carbon single bond. Okay. Next, if you observe from this side, now which is the front carbon? This carbon, no. Therefore, this is a front carbon. We take here. We are observing from here. It becomes rear carbon or back carbon. Carbon 1, carbon 2, carbon 1, carbon 2. Now this carbon has how many hydrogen? 3 hydrogen. Let us take hydrogen 1, 2, 3. So this carbon also has 3 hydrogen, 1, 2, 3. Now tell me, if you see this structure, what is the position of hydrogen? This hydrogen like this on this carbon, okay, like this. It is also like this. There, how they are exactly? They are exactly parallel, no? Means one behind other like this. And here also same. You see like this. It is like this. They are actually parallel. Means one behind. So it is also same like this, no? Means it has to go like this. If it, sorry, like this. It means this is eclipsed. In eclipsed conformation, all the hydrogens are one behind another. So therefore, due to presence of one behind another, they experience maximum repulsions and it has minimum energy. This is eclipsed. Next, what is the staggered conformation in Sahar's? The vertical line indicates carbon-carbon single bond, same, and I'll keep this is as it is, HH. Then what I do is I rotate this molecule in 60 degrees. If I rotate molecule 60 degrees, okay, this where it comes? So it will be like this, like this, like this. So therefore, by rotating 60 degrees molecule, you'll get this. Now tell me, in this, you see the hydrogen. Now back hydrogen is like this, front is like this. How they are? They are exactly opposite direction, no? Since they are opposite direction, there is almost no repulsion between this hydrogen. Therefore, this is called what? Staggered conformation, and this is eclipsed conformation. Okay. Therefore, among staggered and eclipsed conformation, where the interactions are maximum? In eclipsed. Where the interaction minimum? Staggered. Okay. This is Sahar's projection. Next, even conformations can also be represented by Newman projection. Newman projection. In Newman projection, let us take first a circle which indicate one carbon and one dot which is another carbon. This dot indicate front carbon. On front carbon hydrogens are like this. 1, 2, 3. Okay, front carbon is a dot. So there are 3 hydrogen. Next, the circle indicate back carbon, rare carbon. So on rare carbon, if hydrogens are like this, they are exactly behind, right? Front carbon, rare carbon. So hydrogens are exactly one behind each other. Here also like this, here also like this. Then this is called what? It is a eclipsed conformation in Newman projection. Next is let us take circle is back carbon and dot is front carbon. By keeping front carbon constant, okay, don't disturb front carbon, and rotate the back carbon right side. How many degrees? Rotate same 60 degrees. By rotating 60 degrees, okay, so where the back carbon comes hydrogen like this, no? Now tell me, so what is the relation between these two hydrogen? They are actually exactly opposite, no? Like this, one like this. So therefore, this is called staggered conformation. Next, there are 2 points are important. In eclipsed conformation, one, repulsions are maximum. In eclipsed conformation, repulsions are maximum, energy is minimum. Okay, here repulsions are minimum. No. Repulsions are maximum, energy is more. Energy directly proportional to repulsion. More repulsion, more energy, less stable. Energy stability inversely proportional. Therefore, eclipsed conformation has maximum repulsion, more energy, less stable. Staggered conformation has minimum repulsions and less energy, more stable. Okay, next. Then eclipsed conformation has more energy compared to staggered conformation. So then how much energy it has more compared to that, which is called a torsional strain. Another term we use here, torsional strain. What is a torsional strain? Torsional strain is, it is nothing but energy. Okay, so the energy of eclipsed is more compared to staggered. The excess of energy or the extra energy which is possessed by the eclipsed conformation is called a torsional strain. Okay, next is dihedral angle. What is the dihedral angle? The angle between two hydrogen, that is theta. Here is 0. So what is the angle between two hydrogen here in eclipsed? 0. Staggered is 60 degrees. These two terms are important, dihedral angle and torsional strain. Then among eclipse and staggered, which has more repulsion? Eclipse. So that is nothing but we call strain. It has more strain. The strain which is more possessed by this staggered, eclipse compared to staggered, which is called torsional strain. Okay. Now due to torsional strain, so this eclipse converts into staggered. Staggered become more stable, less energy. Okay. So this is the conformational isomerism in ethane. Okay. Write quickly. Conformational isomerism in ethane. Right. In ethane, by rotating carbon-carbon single bond, in ethane by rotating carbon-carbon single bond, it forms infinite number of conformational isomers. It forms infinite number of conformational isomers, out of which two are important. One, eclipsed conformation. 2, staggered conformation. 1, eclipsed conformation. 2, staggered conformation. Next, right. Conformational or conformational isomers can be represented by by 1, Sahar's projection. 2, Newman projection. 1, Sahar's projection. 2, Newman projection. Okay, take as it is both. So taken 2, Sahar's and Newman. We're done. Next, right, in eclipsed conformation, In eclipsed conformation, all the hydrogen atoms on two adjacent carbon atoms are, all the hydrogen atoms on two adjacent carbon atoms are exactly one behind another, and they experience maximum repulsions, hence they possess more energy compared to what? Staggered conformation. Next, right. When eclipsed conformation rotated, when eclipsed conformation is rotated 60 degrees, when eclipsed conformation rotated 60 degrees through carbon-carbon single bond, through carbon-carbon CC single bond, it gives staggered conformation. It gives staggered conformation in which all hydrogen atoms are away from each other. All hydrogen atoms are away from each other, and there is no repulsions between hydrogen atoms. There is no repulsion between hydrogen atoms. Hence it is more stable compared to eclipsed conformation. Next point, the extra energy possessed by the eclipsed conformation, then staggered conformation called torsional strain. Next, the angle between two hydrogen atoms of adjacent carbon, called which angle? Dihedral angle or torsional angle. Dihedral angle or torsional angle. The dihedral angle in eclipsed conformation is 0, staggered conformation is 60. Okay, last one, take this potential energy diagram. Potential energy on y-axis, this is rotation. And tell me, so which conformation has minimum energy? Staggered, no, staggered is here. Okay, then which one has high eclipsed? Okay, so therefore eclipsed somewhere here. We take the conformation